In the previous video, we analyzed the calibration, why it is necessary, what it involves, and how it is carried out from a theoretical point of view. In this video, we will cover it from a practical perspective. The instrument to be calibrated is a 4-digit multimeter, which we use as a voltmeter to measure a DC voltage. We are going to calibrate the 20-volt range. We need a voltage generator capable of producing various voltage values within the range from 0 to 20 volts, as well as a reference instrument that is more accurate than the one to be calibrated, which serves as the reference standard. For this purpose, we use a 6.5-digit multimeter connected in parallel to the instrument to be calibrated, so that it measures the same voltage generated by the voltage generator. Here you can see these 3 devices already connected. Next to the instruments, you can see a PC that we use to manage the various calibration steps automatically by means of a program developed in Python. This is common practice in the most modern and well-equipped calibration laboratories. You can also see a thermohygrometer, that is an instrument which measures temperature and relative humidity so that we know the conditions under which the calibration is carried out. As we saw in the previous video, we need to take into account the entire measurement range that we are calibrating. We have therefore set 8 measurement points starting from 2.5 volts, evenly spaced by 2.5 volts. For each measured point, we record 30 values so that we can assess the uncertainty contribution given by the repeatability of the 2 instruments using a type A method. Let's start the program and let it acquire all the values that have been set. At the end of the acquisition, it computes the mean value of the 30 recorded values for each of the set voltage values, both for the instrument being calibrated and for the reference instrument, as well as the corresponding standard deviations from which it derives the standard uncertainty value to be associated with the mean values. The program then assesses the standard uncertainty contribution given by the resolution of the 2 instruments, assuming a uniform distribution of the resolution error, and combines the uncertainty contributions of the instrument under calibration and the reference instrument quadratically, as shown in the previous video, to determine the calibration uncertainty. The table you see here shows the calibration results. In the first column, you can see the value measured by the reference instrument. In the second, the difference between the value measured by the instrument under calibration and that measured by the reference instrument. And in the third column, the expanded calibration uncertainty evaluated with a coverage probability of 95.45%. As you can see, the calibration uncertainty remains constant. The reason is that the dominant contribution to uncertainty for these instruments is due to the resolution of the instrument under calibration. These operations implement the first step of the calibration process. We now need to address the second step, that is, how to obtain a measurement result starting from the reading provided by the instrument under calibration. And this applies not only to the values considered in the first phase, but to every value that can be measured by the calibrated instrument within that measurement range. To do this, it is useful to plot on a graph the deviations between the value measured by the instrument under calibration and those measured by the reference instrument. These are the values in the second column of the table we saw earlier, which you can see in this graph, where the measured values are shown on the x-axis. On the same graph, you can also see for each point vertical error bars whose half-width is the expanded calibration uncertainty shown in the third column of the table we saw earlier. As you can see, we cannot say anything about what happens outside the measured values. However, by looking at the graph, we notice that the deviations follow an almost linear trend. This observation suggests calculating the line that best fits the deviations obtained. You get the graph you see here, in which the regression line is shown as a red dashed line, and its equation is also displayed. As you can see, at the measured values, the line remains within the intervals built from the expanded uncertainty, thus proving that the values obtained from the equation of the line are compatible with those obtained from calibration. Therefore, given a measured value different from those considered during the first step of the calibration, it is possible to compute the deviation starting from the equation of the line. For example, if the calibrated instrument gives a reading of 13.2 volts, from the equation of the line, one obtains a deviation delta equal to minus 1.88 millivolts. This is the correction to be applied, and therefore the value to be attributed to the measure is the one you see on the slide. The expanded uncertainty to be associated with the corrected value in this case is the same as that associated with the other values, since it depends solely on the resolution of the instrument. In more general cases, interpolation is also used to assess uncertainty. Deviations do not always behave linearly, which is fairly typical for multimeters, but not for other instruments. It is therefore necessary to assess whether they can be interpolated by other functions, for example quadratic or exponential ones, or whether more calibration points need to be considered, and then proceed with piecewise linear interpolations. To summarize, we have seen with the practical example how to carry out a calibration. The steps we have seen are the essential and most important ones that have helped us to understand what needs to be done in the first step, where the measured values and their respective uncertainties from the instrument under calibration and from the reference are related, and in the second step where these values are used to correct the measured values and, as recommended by the VIM, obtain a measurement result starting from an indication.